Hello everyone, and I welcome all of you to another video of physics dedicated to physics. And today we are going to study scalar product of two vectors. The series that I'm going to begin from this video onwards, this is a part of electricity and magnetism course which is taught in BSc Physics Semester 1. It's there in the syllabus of Punjab University, Chandigarh, as well as Punjab University, Patiala. This is the very first chapter which is there in the paper called Electricity and Magnetism. So the starting is all about just revising what we already know about vectors. So the initial topics are simply the review of vector algebra, which we study from class 11th physics. Plus, in the by the end of the chapter, we would be having some new topics as well introduced. So I am going to start with this chapter, vector analysis. So this chapter is about vector analysis. The topics that I'm going to discuss now would be dealing with vector analysis chapter, and the initial topics would be simply a review of vector algebra. So let's start with scalar product of two vectors. So please keep this in mind that this lecture series that I'm going to make, this is for undergraduate students, for BSc students, semester 1, and these videos are particularly for paper electricity and magnetism. We know what are vectors. Vectors is a quantity which has both magnitude as well as direction, and we often denote it by some arrow. And a vector, it has a magnitude, especially the length of the vector tells its magnitude, and the arrow, wherever it is heading towards, it tells us the direction. We all know about what are vectors and scalars. So for undergraduate students, they should have the basic knowledge of what are vectors and scalars. So directly I'm going to start with scalar product of two vectors. We know about vectors, and now we are going to discuss about scalar product of two vectors. Let's start. Now here you can see in the diagram that there are two vectors and they have been joined. Whenever we have to find the scalar product of two vectors, we have to bring them close to each other. Suppose these two vectors were like B was here and A was here. But if we have to find the product, if we have to find any relation between these two vectors, we have to bring them closer. We have to join these two vectors. And that's why here in this picture, these vectors have been joined. So what we will do, we will pick these, we will take this is our B vector, and then we will take this like here and we will bring it and place it closer to B, so that both vectors, they are in contact with each other. Whenever we have to find any relation, any product, or any sort of mathematical operation we have to perform between any two vectors, first step is to bring those vectors close to each other to make a contact between those two vectors. And how do we make the contact? That again has its own properties. But here, just remember that we have joined the tails of two vectors. Usually, for a vector, we know that the vector is represented by an arrow. So arrow is also called head, and the other side without arrow is known as tail. So this vector B is having arrow here, and this portion is its tail, and this vector A, its arrow is here, this is its head, and this is its tail. So we have joined the tails of both the vectors. So the way we join the two vectors, they have a meaning, a very significant meaning, which we would get to know in forthcoming topics. And for example, I can tell you that the resultant of two vectors has a lot to do with how we join the two vectors. Whether we are joining the tail of one vector to the head of another vector, or we are joining the two vectors by their tails. The whole concept, the whole calculation changes. This happens when we find the resultant of two vectors. And students must have studied this in their 11th or 12th class physics course. Okay, so here we have joined the two vectors by their tails. And now we have to find the scalar product of these two vectors. Now, whenever we join these two arrows, they would definitely form some angle. There would be some angle forming between them. So we have to be concerned with only the angle which is forming between them and not the angle which is forming to the exterior of them. See, this is also the angle which is forming between these two vectors, but we have to take care of the acute angle and not the obtuse. Just leave the obtuse angle whichever is forming. We have to look for acute angle whenever we join the vectors to form scalar product. Thus, the scalar product, or we also call it dot product, of two vectors A and B is defined as the products of the magnitudes of the two vectors and cosine of the smaller angle between them. So all we have to do, so this is the representation. We represent scalar product by putting a dot between the two vectors. So we also call it dot product. So A dot B, or the scalar product of vector A and B, is equal to product of magnitude. See, these both are magnitudes of vector A and B. These are the magnitudes. And product of what? Cosine of smaller angle between them. See, we know there are two angles forming. One is the obtuse angle and other one is this one, the acute. So we have to look for smaller angle. So which is smaller, acute or obtuse? Obviously acute angle. So we have to take care of the smaller angle between the two vectors. So no matter how you join the two vectors, we have to look for the smaller angle between them, and the cosine of that angle multiplied with the magnitude of those two vectors would give us the scalar product of dot product of two vectors. So this is the formula that we have to keep in mind. A dot B is equal to magnitude of A into magnitude of B into cosine theta, where theta is the smaller angle between vectors A and B. Then the other thing that we have is that this scalar product is a scalar quantity. Scalar quantity means the answer, the result of this product would be a scalar itself. It won't be a vector. The result would be having just a magnitude. How? Let's take one example and see. Here we have the example. Suppose vector A is 4I cap plus 3j cap. We are considering two-dimensional vector. We have not considered the third coordinate. And let's vector B be 3I cap plus 4j cap. And the theta, the angle between these two vectors, let that be 60 degree. See, if these two are joined, we can consider this angle to be 60 degree. Looks almost like 60 degree. And now we have to find A dot B. So we know A dot B is magnitude of vector A multiplied by magnitude of vector B into cos theta. Now, how do we find the magnitude? See, magnitude of anything, suppose we have any number, any xi cap plus yj cap is there. So its magnitude is always under root, square root of x square plus y square. We square the components and then we take the square root. This here for a it will be 4 square plus 3 square. This, and then for vector b it would be root of 3 square plus 4 square, and then cos 60 degree. What do we get? This is 16 plus 9, and here this is 9 plus 16, and cos 60 degree is 1 by 2. This is root 25, and this is also root 25, and here we have 1 by 2. That means we get 5 and 5, and here 1 by 2. 5 5 is 25, 1 by 2, and this gives us 12.5. And this is the answer. This is a scalar quantity. We have not got the result in terms of I cap or j cap. If we obtain the answer in terms of I cap and j cap, that means we have obtained a vector. But here it's simply a number. This is a number. That means it is a scalar quantity. So by this we conclude that scalar product or dot product of two vectors gives us a scalar quantity. And this is the formula that we have to remember. Now let's discuss the properties of scalar product. First property is that scalar product of two vectors is commutative. What is the meaning of commutative? That means if we have two vectors A and B, then the scalar product of these two vectors is represented by this thing, A dot B. We use dot. Now this product is commutative. That means this is equal to B dot A. No matter whether you write A first and then B, or you write B first and then A, the answer is going to be same. Why is it same? Because all in all, we have to find the magnitude. We know that the formula of this A dot B involve magnitude of these two vectors. And magnitudes are what? They are simply numbers. So if you multiply two numbers, if you multiply 2 into 3 or you multiply 3 into 2, after all you will get 6, nothing else. That's why the scalar product of two vectors is commutative. Next property is scalar product is distributive. Suppose we have three vectors, vector A, B and C. So what is the meaning of distributive? Suppose we are taking vector A and we have vector B and vector C. Suppose we add vector B and C, and then whatever the result is, we are having its dot product with A. How we will solve this? First we will add B and C, and then we will multiply, or then we will take the dot product of that answer with vector A, and the sum of two vectors is a vector. So this would give us a vector. So dot product of two vectors, obviously we should get a vector, but now this is distributive. You can distribute vector A over both B and C. This is the meaning. How? This simply looks like the way we do the normal calculation of multiplication. Suppose we have any number. We have 2, 3 plus 4. One thing we can do is that first we take 2 and then first we add these two numbers and then we multiply it with 2, which gives us 14. Other way is what we can do, we can distribute 2 over both 3 and 4. We can multiply 2 with 3 plus, as plus is there, and we can multiply 2 with 4. This would also give us the same result. 2 3s are 6 plus 2 4s are 8. That will also be 14. So this is the meaning. This is the simple representation of this portion. So this we can write this as A dot B plus A dot C. This is the meaning of distributive. You can distribute a vector over any other vectors, whatever are there inside the bracket. And one more thing, that the operation between those vectors should be either addition or subtraction, only then, because that would give us a vector. Next property is the dot product of a vector with itself is equal to the square of its magnitude. That means suppose we have a vector A and we are taking its dot product with itself, dot product with A. So the answer would be equals to, that would be equal to square of its magnitude. What is the magnitude? Usually for a vector we represent its magnitude by simply the letter itself. See, A with an arrow overhead is a vector, but simply A means magnitude. And here we say the dot product of a vector with itself is equal to square of its magnitude. Let's see how. Suppose vector A is 4i cap plus 3j cap. Now we have to take the dot product of vector with itself. So this is suppose the vector A, and we have to take the dot product of vector A with itself. So if we superimpose, that means we have to take another vector A, but both vectors are of same nature. They have same magnitude and same direction. I'm considering same vector. So what will be the angle between these two vectors? 0 degree. 0 degree is the angle between them because we are considering same vector. So if this is the case, now let's see. A dot A means magnitude of A, and cos theta. And here theta is 0 degree because either we say that both are parallel vector, but not even parallel, they are the same vector. So same vector superimposing over one another, the angle between that vector, if we are considering the vector is having product with itself, so the angle between the vector would be 0 because there is no other different vector, it is the same vector. The angle is always 0. And how to find this magnitude? We would write 4 square plus 3 square, and then again 4 square plus 3 square, and then cos 0 degree. This would give us 16 plus 9, 16 plus 9, and what is cos 0 degree? This is 1. And here we have 25, and simply 25. This is the answer by dot product. And this states that this would be directly equal to square of magnitude. So if we have to find magnitude of A, what is magnitude of A? Magnitude of A is under root 4 square plus 3 square, that is 16 plus 9 under root 25 is equal to 5. And square of magnitude means 5 square, which is 25. And these two are same. See, 1 and 2, these are same. So by this we conclude that whenever we take dot product of a vector with itself, that would be equal to square of its magnitude. Next property is dot product of two perpendicular vectors is always 0. That means if we have two vectors, then their dot product would be 0 if the angle between them is 90 degree, if the two vectors are perpendicular to each other. Why so? Because the formula says A dot B is equal to magnitude of A, magnitude of B, and cos theta. And cos 90 degree is 0. So that's why if you will multiply 0 with anything, any number, the answer would be 0. And also the coordinate axis that we consider, and we say that this is the x-axis, this is the y-axis, this is the z-axis, and the unit vector we consider to be I cap, j cap, and k cap. So if we are considering coordinate axis, and we know I is perpendicular to j, j is perpendicular to k, and k is perpendicular to I. So if a dot product involve these two vectors, then we would get 0. So I cap dot j cap is 0 since I is perpendicular to j. J cap dot k cap is 0, j is perpendicular to k. K cap dot I cap is 0 since k is perpendicular to I, and otherwise also since dot product is commutative, so this also implies j dot I cap would also be 0 because we have just stated the very first says scalar product of two vector is commutative because dot product is commutative. Similarly, we can write for this k dot j would also be 0. And similarly, I cap dot k cap would also be 0. So if two vectors are perpendicular to each other, the result would be 0. Fifth one is dot product of two vector in terms of component of the vector can be expressed in certain way. Now, whenever we express a vector, we express it in terms of components along x-axis, y-axis, and z-axis. That's why we use I cap, j cap, and k cap. Suppose we have a vector A, and it would be something. So whenever we have, it would be, if it's a 3D vector, it would be having some component with I cap, some component with j cap, and some component with k cap. Similarly for vector B, same thing would be there. So anything, whatever is there along with these I, j, k's, they are basically components of this vector along x, y, and z axis respectively. Anything with I cap is component along x-axis. So we can mention it as ax. That means whatever it is along x-axis. Similarly, here we can write bx. For j cap, we have ay, by. See here, this could be a number. After all, it's a component, and component is always a number. So this could be a number 2i cap, 3j cap. But in general, what we say that whatever is with I cap, that is the component representing x-axis. Similarly, for j, it's y-axis, and with k, it is the component along z-axis. So if this is the representation, this is the general representation. After all, whenever you have to represent any vector, this is the general representation of a vector. So this is the representation, and if we take the product now, how does the product take place? How does it happen? First, we are going to write this thing as it is. This whole is getting dot product with this whole. And now I component only acts with I component. It only interacts with I component, we can say. Because we know when there is dot product, we have done this, that dot product of two perpendicular vector is always 0. So if I interacts with j or k interacts with j or I, the answer would be 0, because they only interact with their own self, their own type. They don't interact with others. And that's why I will only interact with I cap. J will only interact with j cap. K will only interact with k cap. Why? Because if I interacts with j, and we know there is dot product, so I cap dot j cap is 0. J cap dot k cap is 0. K cap dot I cap is 0. So all we are left with is ax bx plus ay by plus az bz. This is very simple. We need not to multiply each and every time and make ij's all 0. The product of I with j or j with k is 0. We need not to do that. We only need to remember that if there is a vector something like that and there is dot product between them, all we have to do is just multiply similar components. Multiply the x components, then put the required sign. If it's a plus, then put plus, and then multiply the y components, that means the jj caps, and then multiply the k component, which is the kk caps. So this is the expression that we should remember. Next is the magnitude of vector in terms of its component. That is how to represent the magnitude of a vector. Well, we have already discussed it. Here I showed you how to find the magnitude of vector. See here. Here we have found the magnitude of vector. Okay. And how we have done that? The vector was 4i cap plus 3j cap. So 4 is the component, 3 is the component. 4 is the component along x-axis because it is with I cap, and 3 is the component along y-axis because it is with j cap. So how do we find the magnitude? The magnitude is simply square those components, add them, and then take the square root. And this is what I'm going to represent here now. That this can simply be expressed as, we can mention a, magnitude of vector a can be written as a, or it can be written like this. Both way it means the same. Either a vector with an arrowhead enclosed between two bars, or the letter itself represents magnitude. So this can be done as, we now know that ax, ay, and az are the components of vector a. So this would be ax square plus ay square plus az square. And we can apply this to any vector, be it any number, and we can simply substitute the number and find the magnitude. The last one is angle between two vectors. How to represent that? Now we know that if we have two vectors A dot B and their dot product is equal to magnitude of A into magnitude of B into cos theta, where theta is the smaller angle between A and B. We already know this now. We can also write it as AB cos theta because A and B simply represent the magnitude. Now what if we have to find cos theta? How to write this A dot B? Now from point fifth, we know how to write A dot B. A dot B is AX BX plus AY BY plus AZ BZ. So let's write down. So I just mentioned here that from point fifth, A dot B is AX BX plus AY BY plus AZ BZ is equal to AB cos theta. Further, we can write AX BX plus AY BY plus AZ BZ is equal to AB. What we can write, see here, this is our A vector and that can be expressed in terms of its component like this. So we can write it here also. So from point 6, we can write here AX square plus AY square plus AZ square, then BX square. Similarly, we can write for B vector BZ square, and then there is cos theta. So let me mention that this comes from point 6. Okay, from point 6. Now it's easy. Now we have substituted everything, and in reality, if we'd have any vector, these A and B's would be some numbers. So we can find our cos theta. So this implies that cos theta is equal to AX BX plus AY BY plus AZ BZ upon square root of AX square plus AY square plus AZ square and into square root of BX square plus BY square plus BZ square. So this was the seventh property. So we have studied all these properties of scalar product of two vectors. In the next video, we will discuss vector product, also known as cross product of two vectors. Thank you for joining me today.